Welcome everyone to today's talk at the S3D seminar series. I'm super excited to introduce our speaker, Professor Amulya Yadav. Professor Amulya Yadav is an associate professor in the College of Information Science and Technology at Penn State University. He's the director of the RAISE Research Lab, and also he's the associate director of the Center for Socially Responsible AI at Penn State. So his research is on responsible AI and AI for social good. We know each other for a long time. We were in the same PhD. We were in the same PhD lab. So a lot of I witnessed how he grows to become such a great, a successful researcher. He has done amazing work working with nonprofits, building AIs that can actually be deployed in the real world. And he, not surprisingly, won a lot of awards for his work on these AI solutions for public health and wildlife protection in the wild. And yeah, we're with that. Let's welcome Amulya for his talk.
Thank you, Faye. Thank you for that kind introduction. I am audible to everybody, right? So I don't need a microphone or anything. Okay. So if I stop being audible, just tell me. So today I'll thank you for having me here. I'm really excited, and I'll talk about some recent directions in explainable AI that we've taken in the recent past. And basically, I'm gonna, as Faye mentioned, I'm really interested in AI for social good work, and I'll tell you a story today about how doing research in AI for social good, this entire area, is really challenging. And sort of our attempts at trying to sort of mitigate some of the hardships that people face when they do research in AI for social good research, right? So let's start the story. Basically, I guess I don't need to elaborate this point to this audience. AI has pervaded a lot of aspects of our day-to-day lives, right? From recommendation systems in Netflix and Amazon to AI playing board games better than human beings to driving our cars for us on our roads. To everybody's favorite toy at the moment, ChatGPT, right? But the question that I'd like to ask you guys is who's really benefiting from these AI applications that are being developed? And what I posit in this talk is that whether or not you can enjoy the fruits of AI are really dependent on whether or not you can get access to high quality internet, right? Because all of these tools and technologies that we think about, most of them are predicated on you having access to the internet, right? And a lot of people on planet Earth don't have access to internet, let alone high quality internet. So these are World Bank numbers. One out of every 3 people on planet Earth do not have access to. They've never ever been on the internet. So this is not infrequent access. They have not seen what the internet looks like. And who solves their problems? Are their problems similar to the ones that are being solved by big tech when they create these tools like ChatGPT or Google Maps and this and that, or are they different kinds of problems? Transitioning to low resource communities, it turns out that there are these lots of communities around the world which are low resource, and they have very different kinds of problems which have largely been neglected by AI and big tech, by the community of AI and big tech. For example, just to give you an example, a couple of examples of the low resource communities that we've worked with. Pregnant women in rural Kenya, they have issues about getting access to high quality healthcare in their local vicinity because there are not a lot of doctors or gynac doctors, OBGYN doctors in rural Kenya that are available to them. And that's their problem. That's one of the many challenges that this community faces. Similarly, subsistence farmers in India, among the many challenges that they face, one of the problems is they don't have enough information about what they need to do in order to get a successful crop, right? How do they maximize their profits? How much water does their crop need? Is their crop or is their farm at risk of getting infested with some kind of insect? And therefore, when should they be spraying insecticides? When should they be planning for irrigation, etc.? And they don't have access to this information. Homeless youth in Los Angeles, again, one of the many challenges that they face is that they're extremely prone to diseases such as HIV and other sexually transmitted diseases, and they don't have awareness about what do they need to do in order to keep themselves and their community safe from these diseases. So these are some of the problems that these low resource community faces, and who sort of solves these problems, and that's where we try to step in. So the RAISE lab at Penn State, we try to effectively use AI and machine learning as a force to solve the problems that are faced by these low resource communities. And sort of our ethos is, well, sitting in Penn State, I cannot assume that I would know what their problems are. So we collaborate a lot with non-profit organizations around the world, trying to understand what are the real problems that afflict these communities and what are the real problems that need to be solved. And then once we've identified these problems, we sort of go back to the drawing board, go back to our research desk and try to develop AI solutions that would work for these nonprofits. While we are doing this, we are in continuous collaboration with these nonprofits so as to make sure that we are not making modeling choices that are not going to be reflective of real world constraints and challenges. Because eventually, once these tools are developed, we would really want them to get deployed in the real world. And we would also like to then measure whether or not these tools actually had a measurable impact in terms of some real world metrics that the nonprofit cares about, that we care about, right? But is it really as simple? Is it really as simple as, once you've developed an AI solution that you can just go about deploying that AI solution? So, as I'm going to argue, it's not. I've been in academia for almost 11 years now. I've worked on numerous AI for good projects, but I've only had 3 successes, where I'm really defining successes in a very narrow way. What I mean by a success is that we sort of worked with a nonprofit, identified a real world problem that they were interested in, and we thought we could contribute to. We developed a solution that they said was, they would be willing to sort of adopt, that sort of works with them. But we either never got to deployment, or if we did get to deployment, then we were not able to measure how well did we do in the real world. So if all of these things happen, that's what I call that's what I'm calling a success, right? And so out of all the projects that I've worked on over the years, we've only had 3 successes with this narrow definition of success. So, of course, all the other projects, while all of them did lead to some, good quality papers. So in the sense of that metric, we were successful. But that's not what, what we really care about. What we really care about is having impact on the ground, and all the other projects had 0 impact on the ground because either they were not deployed, or if they were deployed, we were not able to measure them. So why is this happening? Why am I spending so much time inside this field trying to develop AI solutions for nonprofit organizations, yet I rarely succeed at actually deploying things that do work and make an impact in reality, right? Well, it turns out that there's a secret bridge that goes between development of AI solutions and deployment of AI solutions, and that needs to be crossed. This bridge needs to be crossed, and while you're on that bridge, you need to convince the stakeholder of the merits of your AI approach. And this is easier said than done in many cases. So what I'm going to do in this case, in today's talk, is I'm going to convince you of how hard can it be to convince the stakeholder by presenting to you 3 case studies corresponding to 3 nonprofit projects that we've worked on. And we try to quickly go over them to sort of illustrate how difficult it can be. So let's start. So case study 1 is ML for locust swarm forecasting in East Africa. Who were we collaborating with? We were collaborating with the United Nations Food and Agriculture Organization, and also with a nonprofit called Plant Village, who was working with the UNFAO to develop some sort of apps for the UNFAO, right? What was the problem? The year was 2020. East Africa was experiencing the worst desert locust crisis. What are locusts? Locusts are these destructive pests that will eat almost anything organic that comes in their way, right? They'll eat crops, they'll eat leather, they'll eat carcasses of animals, whatever comes in their way. And they're extremely, they move very quickly, they eat a lot of things very quickly. And so what happened is in 2020, this locust outbreak, or these locust swarms, destroyed 40% of the food that was to be produced in East Africa that year. And this was the year that COVID hit. So supply lines were already stretched. It was already very difficult to transport food from one part of the country to other parts of the country, right? And on top of that, the food that was to be transported was gone, right? So what the UNFAO wanted to do is they wanted to generate locust swarm forecasts. They wanted to forecast where these locust swarms are headed next proactively, so that the UNFAO had a limited amount of locust spray that they wanted to send to different counties in East Africa, so that this locust spray can be proactively sprayed on the farms in that area before locust swarms come in, so that the damage that's going to happen because of those locust swarms can be minimized, right? And they want to be sort of cautious with, they don't want to send their locust spray to the wrong areas, whether there are not going to be any locust swarms that hit that area, right? So what did they need help with? I guess Plant Village, as part of a collaboration between them and the UNFAO, they had developed this smartphone application that they had so they're in the business of developing apps, and they also are in the business of distributing smartphones to smallholder farmers in East Africa. They've distributed smartphones to almost 500,000 farmers in East Africa, right? So on these phones that they distribute, they sort of download this app for them. And what this app allows them to do is, or it allowed them to do is, if I'm a farmer in East Africa and I go out of my home and I see a locust swarm in front of me, I can take out my phone, take a picture, it's geocoded, and I record, and that gets recorded as a positive locust observation that there was a locust swarm here today, right? Or if I go outside of my house and I don't see a locust swarm, again, I can take my phone out, take a picture, it's geocoded, and that would be recorded as a negative locust observation. But this is all voluntary. These people, these farmers are not being incentivized to provide these reports. And as you can imagine, what that leads to is you get heterogeneity of data collection across space and time. There are some urban centers from where you get lots of data. There are entire dark spots from where you have very little data about whether there are locust swarms there or not. Even though there might be lots of farms there, we don't know anything about what's happening there because nobody chose to report data from these areas, right? And also there are specific days on which people are reporting lots of things. Again, there are other days on which people are reporting very few things. So we wanted to work with this data to generate observation or forecasts for where these locust swarms are headed next. I guess so I'm not going to go into all the details of these papers because we have a lot to cover. I'll just give you high-level flavors of what we did. So the first order of business was, how do we represent this data? And I guess what we did is we sort of framed it as a binary classification problem. If we wanted to predict whether there's going to be a locust swarm at this blue location on day T, some day T, let's say today, what we'll do is we said, let's count in a 7x7 grid that is centered on this blue dot. Let's count all the number of locust presence and absence reports that have been counted in each of these sort of small grid cells in the nearby vicinity. The idea being that if locusts have been observed in the nearby vicinity, then there's a good chance that they can hit this blue dot area, tomorrow or day after tomorrow. And we don't rely on just numbers from today. We sort of use these numbers, these locust presence and absence numbers from yesterday, day before yesterday, 3 days ago, 4 days ago, and so on and so forth. That's a hyperparameter that we sort of tune. So maybe we have 10 days of historical data about how many locusts were found and how many locust presence and absence reports were reported from this grid. So that was the first thing that we did, but we still had a huge data sparsity issue, right? We were going to generate highly inaccurate predictions for a lot of areas because we just didn't know what was going on in those areas. So we wanted to augment the data on top of this as well. And I guess the second thing that we did is we came up with novel data augmentation schemes. So the idea, again, I'm not going to go into the exact specifics of or the theory behind it, but basically the intuition is, let's say in January 2020, there was a positive locust observation that was reported here. And in March 2020, there were positive locust observations that were reported there at these other locations. And there's a certain probability, because you're not identifying this is locust swarm number 1 and this is locust swarm number 2. There's a certain probability that this swarm is this exact same swarm in March 2020, which means that in February 2020, they must have been somewhere in the middle. But of course, we're not sure about this because we don't know for sure whether this swarm is this swarm or it could be some other swarm. So we sort of come up with a incentivization, a sampling scheme that allows us to create more data that sort of tries to respect this constraint. The high-level intuition is if I see a locust swarm in Pittsburgh on Monday and I see a locust swarm in Philadelphia on Friday, then there's a good chance that it might have traveled to State College on a Wednesday, right? But that's only a chance, so we don't know for sure that that's going to happen. So we used we developed some sampling schemes that followed this intuition to add more data and to sort of make our data more equitable across geographic areas and time, so as to remove this problem of data sparsity. And then we developed a multimodal deep learning architecture. We used this locust representation data, this more complete locust representation data. We sort of paired that up with environmental features because, for example, soil moisture. Locusts lay their eggs in sandy soil. So if they're at that sort of stage of their life cycle, if you want to predict where locusts are going to head next, if they're in the stage where they're going to lay eggs, then they're going to be heading towards area with low soil moisture. And hence soil moisture can be a huge sort of predictor of where, when you're trying to predict where locusts are and where they're going to go next. Similarly, wind speed at 10 and 50 meters. Locusts try to move with the wind in an effort in trying to conserve energy. So they flow with the wind, and therefore the wind speed and wind direction at certain elevation levels can also be a huge predictor. So we sort of combined these things. This is pretty straightforward. And then we got something that looks on the right? So we got a heat map. Dark red means we are highly likely. These are 3-day forecasts. So this is what we are predicting is going to happen 3 days into the future, right? And dark red means we are predicting that there's going to be lots of locust swarms in these areas. Light red means that there's a less likelihood that there's going to be a locust swarm in these areas. And the crosses and the circles, they represent actual observations from 3 days later, right? So of course it's not a perfect system, but as you can as you can see, it's working out in many areas. So this sort of blue dark red cluster where we were predicting there are going to be locust swarms 3 days later, we actually observed lots of positive sightings of locust swarms from this region, and there's this sort of middle region where we are predicting lesser sort of likelihood of locust swarms there. Indeed, 3 days later, lots of people sent in reports of negative locust observations. So it was working well in simulation. In simulation, we found that we were doing 10 to 15% better in terms of predictive metrics over the current physics-based model that was used by the UNFAO, but it never got used. Why? Well, because the UNFAO, they were using this NOAA model for locust swarm forecasting. This NOAA model is a physics-based, it's a model that is used to simulate how air particles move about in space, right? And that's been retrofitted. The inventor of NOAA is an in-house expert at the UNFAO, and they've retrofitted the NOAA model to do locust forecasting. And basically, when we presented these results to the UNFAO, to this expert, they could not believe that their model, that this neural network kind of thing can beat their NOAA model, which is more physics informed, I guess. And they really wanted to understand, please explain to me why can your model do better in this situation as compared to in this situation? And we didn't have a good answer for them, right? We gave them coefficient values. We gave them whatever we could in terms of trying to open the black box that our model was. We tried to open it to them, but they just wouldn't listen. It was also a case of us in this particular setting. I almost got the feeling that it was a case of they felt that they had to protect their territory, right? And so basically this model was never used, right? We published an ISKDD paper on this, but that was about it. So that was the first case study. The second case study, moving on to the second case study, this is influence maximization of preventing HIV. Yes?
May I ask, what kind of things did you try here to try to persuade them?
Well, we basically sort of, I guess what we did is, what the kinds of explanations that we provided was that what would need to change in the locust sightings that would change the prediction. So they were saying that it cannot be the case. This is really nonsense. Just to give you an example, that it's impossible that you're predicting high likelihood of locust swarms there, because they're not headed there, right? And what we told them, that if you want us to explain why a model is doing that, what we can do for you is we can tell you, well, what you need to change in the inputs, that if you worked with these inputs instead, then you would have seen lesser likelihood, and you can tell us whether that. And then they were like, no, this does not make sense, and you're not using the right features, and yeah, so yeah.
Then do you try to incorporate those physics informed model into your deep learning?
I guess we never got a chance, right? I mean, we sort of the door was shut on us, and basically the pandemic passed, the desert locust stresses of that year passed eventually, and yeah, we were never able to get into a room with them again. Yes, anyone?
Yeah, I just believe that I think you are right that the input of the data actually was quite wrong, because that is how human being can collect the data naturally. Mm-hmm. If you expect a farmer to report like voluntarily by taking a photo, there must be some misleading and also some kind of wrong data over there, mm-hmm. which may influence the output of your algorithm.
Sure. So I'm not certainly claiming that our algorithm is perfect. I'm also not claiming that I have any knowledge of whether this model, had it been implemented, that it would do any better than the NOAA model that they use, right? So maybe it works very poorly, right? But as my counter argument would be that at least in simulation, right, on historical data, our model was outperforming their model by 10 to 15%. So based on that, you're right that our model comes with its limitations, that it is human collected data, it's voluntary, there's no incentives. And yes, I mean, they might be misreporting. And in fact, we do have evidence of some misreporting. I think initially when this data collection started, there were some people who sort of incorrectly thought that, if we send in more reports, we're going to get some amount of money. and so therefore, some people, what they did is they sort of put a picture of a locust as a wallpaper on their computer, and they took a picture of that wallpaper, and it's very obvious, it's a computer screen that they've taken a picture of, and there's a locust there, so that has happened, and yes, so I'm in no way sort of claiming that my model is actually superior to their model, but I guess what I'm trying to say is we never got a chance to find out. Is my point.
Yeah, I think the improvement point was to how to collect the data at the very beginning. Have you ever thought of, for example, spotting lotus from images from like TikTok or like public photo galleries like Instagram? Because these guys sharing those kind of information voluntarily, they make it for fun, and you have open.
That's a good idea.
Widely used.
I don't think we did try that. Yeah, but that's a cool idea. I guess that's a hypothesis in the sense that that people who live in these areas, that there's going to be a large amount of social media signals that can pick up on where there are locusts and where there are no locusts. But yeah, that would be a cool idea, I mean, that's certainly worth trying.
Yeah, those were just the regular photos they take for their families, and they are sitting on the farmland, and there's lotus like in the picture, and you spot it.
Sure. Yeah, I mean, that's an idea. Yeah. Yes.
So if this gets deployed, and if they would have now, it would be better in terms of predicting, and they would have used more sprays. Then this would change the distribution of where the locusts go and so on because of the sprays. So does your model somehow also account for such kinds of distribution shifts? And does the NOAA model, can they account for such distribution shifts?
The answer to both is no. For both models, they don't account for distribution shifts. Neither does our model, nor does their model. And you're right, it is going to change the distribution shifts of where the locusts are going to go, but we don't take that into account. Yeah. But good question. Was there any other question before I move forward? All right, so this was case study 1. Case study 2 was, I guess, in this case, we were collaborating with 3 homeless shelters. My friend's place, Los Angeles LGBT Center and Safe Place for Youth. Apparently, homeless youth are extremely prone to STI infection. The rates of HIV infection amongst homeless youth are 10 times that of the rates of HIV infection amongst stably housed youth, right? And to sort of prevent that, what these organizations do is that they run these peer-led popular opinion leader interventions. What does that mean? They basically train some youth from within the population of homeless youth, and they train them as peer leaders, where these peer leaders are given information about this is how you contract HIV, this is how you contract hepatitis C, this is how you keep yourself safe, and this is what you do if you think you've been exposed, this is how you keep others safe if you have the disease, this is where you get tested for free, etc., basically, right? So this is the kind of information that they're given, and then they're told, well, now you need to be a leader and go talk to your friends about it. Go share this information amongst your peers, go try to change behaviors of your peers towards safer sex practices. Right, because these are private conversations about sex, about practicing safe sex. They're also given a lot of training about how do you approach these topics if you're talking to someone who's not you're not in a relationship with, for example, right? So what did they need help with? They wanted to understand how to choose peer leaders for this intervention, meaning how do you choose the influencers in these social networks. And so how did we help? I guess we developed some AI tools for them. The challenging part in this project was, so influence maximization is a well-known topic in AI and in computer science in general, right? But what it assumes, for the most part, is that the social network that you have is given to you. But what we were working with is in-person social networks of homeless youth, and it was very difficult for us to map who's actually connected to whom, because we're relying on self-reported friendships. So I might say Tom is my friend. Faye might say Tom is my friend, but maybe there are 5 Toms in the population. and we don't know who's connected to who, which Tom am I connected to? Are we connected to the same Tom? Are we, so that's a problem. So there are some friendships which we may be certain about. There are some other friendships which we may be uncertain about. And what that creates is uncertainty, in the sense that, if I influence C, I train them as a peer leader. And if I'm very certain that C is friends with B, then I can maybe assume in my calculations that there's a good chance that B will also get the information from C. But since I'm uncertain about whether C and E are friends, then I don't know whether should I be wasting my time by influencing node E in case they already have the information, or is it going to be a case of repeated information exposure, or is it going to be the first time that they're going to hear about it? I don't know. So there's uncertainty about whether E will have the information, and that creates challenges with respect to figuring out who should you go after next. Which part of the network do you want to influence next? So I guess what we realized is, we can cast this entire partial observability and this uncertainty as a POM-DP, as a partially observable Markov decision process. Since this was a POM-DP over networks, it was extremely large, and we sort of took a hierarchical ensembling approach. It turns out you can partition this POM-DP into smaller POM-DPs and sort of solve them up and aggregate the results. Yes?
Minor question, how do you decide on the directionality of the edges?
Right. So good question. I guess what the way that these networks were created by social workers is that they asked each person to list out people inside your social. Who do you think, you come to this shelter every day, within the people that you see here, who are your friends? And I'll list down, Tom is my friend, Harry is my friend, and so on and so on. But it's not necessary that Tom mentions my name in their list, right? And therefore you get some sort of a directionality. In many cases, you do have bidirectional relationships if both people mutually think that
If you say that Tom is your friend, then do you assume that Tom can influence you, or that you can influence Tom?
I guess what we assume is that if they say Tom is my friend, we assume that I can influence Tom, right? But you're right, it might be the other way around. So that's the reason for directionality. As I said, most edges that we have in our, we end up collecting our bidirectional friendships, but then every once in a while we do get these unidirectional friendships, which mostly correspond to people who are these who are really popular within the homeless youth circles, right? Everybody wants to think that they are this person's friend, but they have basically, those were the kinds of relationships that we've been captured through these unidirectional friendships, right? So that was one sort of challenge. The other challenge was that in influence maximization, everybody assumes that you're going to be given these probabilities, which correspond to probabilities with which people will spread this information. So for example, if D has information, there's an 80% chance that they'll spread information to node E. But how on earth are we ever going to get these probabilities in the real world, right? That's a huge assumption to make. What's more likely is maybe we can work with the homeless shelter officials and ask them, well, are these people, do you think they're friends, or are they not friends, right? Do they know each other, or do they not know each other? And if they know each other, that sort of covers the spectrum of people being in relationships together. That's one end of the spectrum. Or, they're acquaintances, they talk every once in a while, but they're not best buddies, right? That's another end of the spectrum, right? And so I guess if you know that these people may know each other, then I guess the only thing that we can assume, or a more realistic assumption, is that we don't know what the exact probability is, but we're going to assume that it lies somewhere between 0.4 and 0.9. It's going to be on this side of the spectrum if these people happen to be in relationships. It's going to be on this side of the spectrum if they just happen to be acquaintances, right? And these widths can be sort of adjusted. Those are, I guess, hyperparameters, right? And similarly, if people don't know each other, then the range, I guess we can set it to be wide enough such so as to encapsulate either people not knowing each other at all, they're never going to talk to each other, or they might just, maybe also to model the fact that maybe the homeless shelter people don't know enough. Maybe these people do talk to each other, but they don't talk in the shelter. Once they're out, they hang out together. Maybe so to model that fact, we sort of still assign some probability with to those friendships, right? So there's uncertainty in influence model. How do we deal with this? I guess this entire thing can be cast as a game between an influencer player, the homeless shelter, who's trying to influence these people into good behaviors, and then we assume that we are up against an adversarial nature player who's going to pick that probability from within this range that's going to hurt our influence spread process the most, right? So they're going to pick the worst case probabilities that will diminish our influence spread capabilities as much as possible, right? So we want to be robust against the worst case. And as you can imagine, because these are probabilities, the adversary has a continuous strategy space. It turns out you can come up with a lossless discretization of the adversary strategy space. Again, won't have time to go into that. But yeah, basically this is robustness against worst case influence model. This one we were able to deploy. So we ran clinical trials with approximately 900 homeless youth in Los Angeles. And basically what we said is, we asked them for self-reports of frequency of unprotected sex, right? So at baseline before the study, approximately 30% people in this arm of had reported that they engaged in this variant of unprotected sex, two different kinds. And I guess the blue line is the degree centrality, which has been the status quo for social work researchers. This had been what they had been using. What is degree centrality? That if you want to pick peer leaders, just pick the people who have the most number of connections, who report to have the most number of connections, people with the most number of friends. Those would be good peer leaders, right? So that's what degree centrality does. This is what has been the current or the most prevalent modus operandi of social work researchers. And we compared them with Change, which is our AI arm of the study. We had other arms as well, but just talking about one arm. And what we see is that there's a faster and larger decrease in self-reported rates of unprotected sex when the peer leaders were chosen by the AI algorithm as compared to degree centrality. And these results are statistically significant. So there's that. So this was, I guess, deployed, but it was not as straightforward as us developing a solution and them deploying it. We really ran into a hard time in trying to explain to the social work researchers and to the folks at the homeless shelter, why is our POMDP solution and why are these complicated algorithms working better than degree centrality, which is such an intuitive choice for them, right? Why is it the case that degree centrality is not the best thing? So again, we were finding it very difficult, relatively difficult to get them to trust our results. But in this case, I guess we got lucky because we had a champion on our side, right? We had Professor Eric Rice, who had from USC, who had built these relationships. He had been working with these homeless shelters for almost 20, 30 years. He was an expert in youth homelessness, etc. And basically he so they trusted him. They didn't trust us, but he sort of said that I trust these people enough. It's my responsibility if anything goes wrong. I would like to test these systems, and I'd like to stop here and say that this is predominantly and unfortunately the approach that's been taken so far by the AI for social good community with respect to deployment. That we rely on champions, right? We rely on people on the inside who can stick their necks out and try to get our AI algorithms deployed and sort of serve as this intermediary or bridge between the non-profit and the AI researchers, right? And that's not a very democratic way of doing things, right? Whenever I give talks on AI for social good and I get questions, well, how can I help? Unfortunately, the only answer that I can give them is come work with me or come work with Faye, right? Because we've been lucky enough and fortunate enough to have built some connections with non-profit officials and with these champions. But to a young person who doesn't have these contacts, how do they go about getting invested in this space? I'll briefly talk about the third case study, POMDPs for testing policy for COVID, policy design for COVID-19. Very briefly, I'll tell you, this was summer of 2021. Penn State was deciding on, so the NGO collaborators, Penn State in this case, I guess. Penn State was deciding, everything was working remotely. Penn State was contemplating whether they want to open in person for the fall 2021 semester. And they had set up a huge task force to help them figure out, well, can we bring in students from all parts of the country, and sort of, what is the number of infections that we'll end up getting? Because we have a small hospital, will our hospital be able to handle the sort of increase in infections that we'll get? How many tests do we need to procure to be able to sort of manage the sort of rise in infections that we'll get? So they wanted to figure out how many COVID tests do we need to procure ahead of time and how should they be allocated? So the task force was led by epidemiologists, and they were leaning toward the static solution. So they said, every day we would like to assign, based on simulations that they did, SEIR simulations that they did, they said, every day we would like to assign 1,200 tests to the hospital, to the local hospital at Penn State. That's how many tests we would like to send to the hospital. And then every day we will test 1% of the student population out in the streets. So this is asymptomatic testing, people randomly walking in the seats. We'll set up booths and we'll ask them, can you get a test? Can you get tested? This is a random test, right? And that apparently for them was the best solution that they came up with. And what they needed our help with is, well, can AI be used to develop a better policy? Because really there's no need to be static. No need to go with a static solution, right? I mean, if you see the results of the COVID tests, if the number of positive test results start falling, then you can accordingly adjust your strategy so as to be able to catch more asymptomatics, right? And so therefore, in theory, adaptivity should help. And we wanted to answer for them, well, or to give them some proof about how can you be adaptive and how much benefits do you get. And so we created a POMDP solver that generated an optimal adaptive testing policy. We ran some simulations. We sort of, inside the POMDP, the transition model, we kept exactly the same SEIR model that they were basing their simulations on, right? And then at least in simulations, it was doing better, in terms of infections by 30% as compared to the Penn State's official strategy, right? And then we sort of went and had a discussion with the lead epidemiologists, and I only got as far as explaining to them or trying to sort of unroll what POMDP means as a partially observable Markov decision process, and I've learned enough. It's really complicated. I'm not going to base this life and death sort of decision about whether Penn State should open or not and how many tests will keep us safe based on this really sort of high risk strategy that you're putting in front of me. And they said, no, clearly not. We're not going with this. We'll do the static thing because that's simpler. That's easier to defend, I guess, right? If things go south. And so again, the solution was never used. So I guess through these 3 case studies, I've sort of highlighted the myriad of the kinds of difficulties or challenges that we come across when we try to cross this bridge from development to deployment in terms of trying to convince the stakeholder. And I guess also we want to be mindful of time. How much time do I have? 20 minutes?
Till 1 p.m.
1 p.m. Okay, 20 minutes. All right. So yes.
Quick question. So, like for your previous case, what's the reason like they don't want to adopt the policy? Is it because the cost of the too expensive, too complicated?
Too complicated, and too. I guess it was more because the epidemiology team then had to talk to the university leadership, and the university leadership would like to understand what we are implementing on the ground, and to tell them that we're going to use a POMDP, I guess, didn't really fly well with them. That we got to explain that there's this fancy AI algorithm. There's a good chance I might not be able to explain everything about it, but it works well. So I guess basically, to be honest, I did not sit in that room where the talks with the university leadership went. I guess it was right. So, yeah.
That's also my question. So, do they, the policy decision maker, do they need to understand the technical details so that they can make the decision, or they only need to understand, this algorithm, this new method actually is more accurate, can potentially reduce the risk,
So once again, I can't speak for the particular university leadership at Penn State. I guess it varies from person to person. I don't know whether the particular leadership team at Penn State really wanted to know the details or so. So maybe they did, maybe they didn't. But I was interfacing with the epidemiology team, and they said, I cannot take this to the university leadership because this would sound too experimental, right? And this would, basically. So to answer your question, I don't know whether at the top level of administration, do they really need to understand? Do they really care about what is happening under the scenes, or do they just care about end results or end level metrics? I really don't know which is it, right? But yes, what do you say?
So you point out the role of kind of the black box and explainability, which does strike me as being super important in these conversations. I understand that. But when I think about public policy decisions, you can make logical arguments, but you can also show kind of empirical evidence, right? Mm-hmm. And you had simulations.
Yes.
But the challenge is, does the simulation reflect reality, right?
Absolutely.
How well are these things calibrated?
Absolutely.
And so, and it seems like both in the case of COVID and the locust case, people had to make a decision, before you had a chance to really validate the simulation because there was a crisis, right?
Absolutely.
So I don't know. I guess how can we Is it possible that we can do better in terms of making the case from empirical data? And I don't know, I just like to hear your thoughts on that.
No, that's a great point that you bring up. I mean, I think as a responsible AI scientist, if you put me in a very high stakes sort of situation, such as let's say COVID was a really high stakes situation, I'll be honest and I'll say that, inside the POMDP, there are several assumptions that we make, which are assumptions. And I don't really know whether those assumptions are actually going to hold up in state college or for that matter, any city. So therefore, if you ask me, should we be using the system over something that is better? I guess there are two ways to think about it. I don't know whether my assumptions are correct, but then I'm also very sure that they don't know whether their assumptions are correct. Right? So eventually a decision has to be made on incomplete data. The lead epidemiologist at Penn State told me something very, in the pursuit of excellence or in the pursuit of perfect, let's not miss out on the good, right? Or on improving upon what you can do right now with incomplete data. Because I put this question to him, right? How can you be sure that your seer model that you're testing, because it was the case during COVID, almost every group who was working in this space was coming up with their own variant of sort of model fitting, and they would work perfectly, very nicely on past historical data. But if you ask it to forecast what's going to happen, it would work perform terribly. So I was like, why are you confident? What is the basis of your confidence that your model is good enough, right? And he said that it's not perfect, it's not good, but this is the best that we can do with the data that we have, and we have to act right now. So yeah, but yeah, that's a very, very valid point, I guess. I mean, so to summarize, I guess I know that my AI algorithms come with flaws, and I would want to be very, very transparent about those flaws and limitations and assumptions that I'm making in the AI system. When I sort of talk to university leadership, I didn't talk to them, but I would want them to know that these are the assumptions that we are making. This is what we don't know. This is most likely not correct. And then you can take whatever decision that you want to take, basically. Yes.
Have you tried convincing them of any deployment with guardrails? So what do I mean by that? This is something that has worked well for us. That is, if there is a status quo method that they trust, and we'll say that, well, we'll use our method, but it will always be within 15% of this. And so they're not too concerned at that point, and they're okay with experimenting with it.
Good point. And yeah, we didn't try that. At least for these applications, we didn't. I don't think we've had that situation has ever arisen, at least in with the nonprofits or Penn State that I worked with, where we had that conversation. But yeah, that seems like a better way to approach these conversations about trying to convince them that, hey, if our system doesn't work, at least we'll also run either what you're saying or say that we'll have a backup system running. If our system fails, there's a backup option that you can use as well. Yeah, that's a good point. Anybody else? Anything else? All right. So now I sort of talk about explainable AI. So what I want to say is, well, can explainable AI help, especially for young people, right? Especially for people who don't have access to champions and who don't have the resources and the connections that one builds over a long career in academia. By no stretch of the imagination do I have a long career in academia, so I'm not one of those people. But yeah, can explainable AI go some way, right? In trying to convince stakeholders, right? And I was a novice in explainable AI 5 years ago, and I'd never worked in explainable AI, and so we started surveying the landscape. And what we found is that a lot of the methods that we looked at, talked about, presenting coefficient values and weight values. And what we argued was, or what we reasoned, these are subjective opinions of mine. I mean, different people feel differently about these, but my opinion is that, these talking about coefficient values and gradients, etc., would be better suited for people who have some basic running knowledge of machine learning and AI. But our non-profit people, the people who we tend to collaborate with, they wouldn't be good people to sort of provide coefficient values, and because we tried that, right? I mean, we tried sort of providing coefficient values to the UN FAO expert, and that didn't go very well. The other limitation that we found of explainable AI work is that almost all of it assumes that you're trying to explain the predictions returned by an ML model, which is black box. So it's somebody else's model. You're trying to explain the predictions for somebody else's model that has already been trained, that is out there, and you can only assume black box access. So for example, let's say you're trying to explain Amazon's recommender system. Now, I can't assume access to Amazon's recommender system. I can't assume access to training data, etc. The only thing that I can assume is maybe I can use it. I can pass an input, see what it recommends to me, right? So input and output. And this can be anything. This need not be Amazon's recommender system. This could be almost any AI sort of model which we don't have access to. And this is the setting that most XAI work focuses on, right? This is 99% of work in XAI. But this is not our setting, right? Because our users our end users are non-profit people who are not ML experts. And furthermore, we don't need to limit ourselves to the post hoc assumption, because in this case, we are the ones who are developing the ML algorithm or the AI tool, right? So we know our training data, we know our model internals. So the question that we ask ourselves is, well, can we do better? Can we utilize the knowledge of our ML model or our AI tool to be able to generate better, more high quality explanations, right? That's what we want to try and answer. So again, a subjective choice, amongst the different kinds of explanations that exist, or different qualitative styles of explanations that exist, the one that we sort of narrowed down upon is counterfactual explanations, because I thought that this makes most sense from an actionability perspective, it makes most sense to average end users. So what are counterfactual explanations or contrastive explanations? Let's say there's a person who's applying for a loan at a bank, right? And they're applying with these features. They're 24 years old, requesting $20,000 for 36 months, FICO score of 600, income is 2,500, and they get denied. Maybe the bank is using an ML model that they say, we don't like your, loan application, you've been denied. As a counterfactual explanation, we would like to provide to them that, if you keep your entire application exactly the same, and you just ask for $4,000 fewer, and you increase your FICO score by 50, as long as you make these modifications and you keep everything else in your application exactly the same, this model would have accepted your application and would have moved you on to the next stage. So this is about providing recourse to the affected individual who's received a negative or an unfavorable decision by an ML model, right? And we would like to create this new artificial loan application corresponding to a new point automatically, in an automated manner, right? So that's what a counterfactual explanation is. More formally, let's say you have a data set, some positives, some negatives. There's some machine learning model, and maybe you're trying to explain why is the prediction on this point negative, right? What you're looking for is another point, an artificially constructed point, need not be in the training data set or the test data set. You're looking for a new point which is on the other side of the decision boundary, right? So you care about two things. You care about validity, which means that the explanation should be valid, which means it should lie on the other side of the decision boundary. And you care about cost of change. So you would want to minimize the amount of modifications that it takes for you to go from here to here, right? Because you don't want to tell somebody that right now you're a high school graduate, get a PhD before you reapply for a loan, and that's a huge sort of investment of time that you're asking them to do. So you want to minimize the amount of modifications that you ask people to make. And yeah, so this is what these two objectives are sort of complementary in some, competing in some sense, and you want to, there's this trade-off between the invalidity or validity and the cost of change that we want to sort of find a sweet spot for. So there's a lot of work that has happened in trying to find these counterfactual explanations. There are non-parametric methods which solve different, and all of them really focus on, there's a validity loss, there's a cost of change loss, you trade them off with some lambda parameter, and then you try to find some X that optimizes this equation, right? And there are also, but these are slow, there are also parametric methods that exist in which you can sort of replace this optimization problem with a let's say a neural network or some sort of a parametric model. And again, you're going to try to optimize these same two objectives. You'll try to sort of tune weights that will find you, that will allow you to minimize this objective, right? Okay, but as I was saying, as is true for all prior work in XAI, the work in counterfactual explanations was also post hoc. It was designed for a post hoc setting, meaning it was designed to be used in situations where you're trying to explain somebody else's model, not your own model, right? But we are not in that world, right? So in the non-profit setting, we are the model developers, and therefore, do we really need to restrict ourselves to post hoc explainability? And I guess we don't need to. And the question is, can we do better if we sort of depart from the post hoc paradigm, right? I would also, I think in our papers, we argue that even though we got interested in the space because of our connections to or our experiences with non-profits, I would argue that these situations are going to become increasingly common in the days to come as with increasing amount of regulation. For example, EU came up with GDPR years ago, and they have a right to explanation. So any EU citizen, if they receive an algorithmic decision, they are entitled to an explanation as to why they got that decision. And similar, California adopted their own regulation. India is in the process of drafting their own regulation, and so this is the future that we are heading towards. And if that happens, if model developers are going to be required by law to comply with the law, they will be required to provide their own explanations. Then the post hoc assumption is overly limiting for such model developers or service providers, right? So far we've been living in a world where explainable AI is a nice to have feature. We care about accuracy, we care about end-term objectives, but on the side, it would be nice to have explainability as well. But in the future, if we transition to a world where explainable AI is a must-have feature, then it would be important for us to sort of extract, why shouldn't we extract the additional knowledge of the model internals to do better, right? So we sort of take the first steps in this direction by creating prediction-aware explanations. We're going to try to create an end-to-end system where we jointly train our prediction system and our counterfactuals, so that this influences the prediction system influences the design of the counterfactuals, and the counterfactuals influence the design of the prediction system, and we'll try to jointly train them. So let's talk about CounterNet. This is basically the first model that does prediction-aware explanations. So this is the architecture. I'm talking about tabular data sets, but you can extend it to image and other modalities of data as well. But let's talk about simple tabular data. It has three parts. There's an encoder, which creates a latent representation. This feeds into a predictor network that creates a prediction. It also feeds into a CF generator network or a counterfactual generator network, which is going to output a counterfactual explanation, right? So the output from this entire architecture is going to be two things simultaneously. We'll get a prediction and we'll get a counterfactual explanation, right? And because we wanted to model this intuition that the counterfactual explanation design should depend somehow on the decision boundary that's being learned, we wanted to be aware of what is the prediction system doing. We sort of created a backwards loop. The final layer of the predictions is fed back as input into the CF generator network, right? And this sort of seems to work well based on our ablation studies. In terms of objective functions, we are co-training or jointly training these two things at the same time. So we care about prediction loss, right? We care about validity loss. We care about proximity loss. These two things are more concerned with the quality of the CF generator network. The prediction losses for the predictor network, right? And the most straightforward thing that you could do is you could sort of combine these three objectives, add lambda parameters, and try to optimize all three things at the same time. Okay, and we tried that. That's the first thing that we tried. We ran vanilla backprop, but it does not work as well. We ran into poor convergence issues. So this is only the validity loss, and that sort of ends up converging to approximately 60%. That means only 60% of the counterfactuals that we were generating were actually valid. They were actually on the other side of the decision boundary, and that's no good. Why was this happening? Well, it turns out that the L1 loss, the prediction loss, and the validity loss, they had divergent gradients. And so if you add them up together as part of the same objective function, they were canceling each other out. Right. So this prediction loss and validity loss, we were able to sort of do some theory that said that they'll always end up having divergent directions. And it is this divergent gradient that is leading to training instability. So to fix that, we sort of did coordinate descent. And I guess we said, let's separate them out. So let's do two steps of backprop. In the first stage, we'll only do a backprop on L1, which is a prediction loss. And then with the updated weights, we'll then take them and do another step of backprop in which we optimize L2 and L3, right? And this helped. So when we did this, now we were getting much better convergence. Now our validity losses or values were up to 95%, right? There was another important issue that we were facing, which was adversarial robustness, which is, so here we are plotting perturbation stability. Higher stability means better adversarial robustness. We want to be higher in this figure for different values of epsilon. And you have two colors here. You have the green color, which is standard CounterNet, which is the original architecture that I've showed you. And then there's this base model, right? And the base model is doing better. What is the base model? So you get the green line if you use this architecture, use the standard architecture. But then we said, let's sort of eliminate the counterfactual generator network, and let's just only look at the prediction network to sort of get at, what are we losing in terms of adversarial robustness if we choose to jointly train these two things together, as opposed to if we were only doing predictions. So if we only do predictions, the blue line is the adversarial robustness, is the perturbation stability graph that we get. But if we sort of jointly train these two things together, what happens is that our the perturbation stability and our adversarial robustness falls. We do poorer. It is more prone to adversarial examples, and that's bad. And why is that happening? I can give you some intuition. In reality, optimizing these three objectives together, prediction, validity, and proximity, that's an ill-defined problem. Why? Because you are trying to find for every point X, you're trying to find an XCF. And normally, if you just optimize for validity and proximity, if you're just trying to optimize for counterfactual explanations, then this decision boundary is fixed. You can't play around with that. That's not a variable, right? And so you have to find a point which lies on the opposite side of this fixed decision boundary. But since we are optimizing all three things at the same time, this decision boundary is also variable, right? So we can cheat basically by finding a better quality counterfactual explanation and making our decision boundary more nonlinear, right? Thereby making it more susceptible to adversarial examples. So this is an example of us. We would, try to, effectively do these weird things. We can practically set the proximity loss to be very low, and still we'll be able to find something that sort of goes between them, right? And that was the cause of perturbation stability. We were able to formally prove this. The real culprit was minimizing L2, the validity loss with respect to the predictor weights. We showed that it increases the Lipschitz constant. There's prior research that shows that, if you have a higher Lipschitz constant, that implies lower adversarial robustness. So to fix that, we don't want to minimize L2 with respect to the predictor weights. So to fix that, what we did is, in the second stage, we chose to freeze weights in the predictor network. So first we did a weight update on the predictor weights, and then we froze those weights. And in the second pass, when we did backprop, we only chose to update the remaining weights in the network, right? And that sort of helped. So when we did that, the orange line is what you get if you do this freezing, right? If you do freeze the weights of the predictor network in the second stage. And what we see is that with that, we are able to get to exactly the same amount of perturbation stability as we would get with the base model. So if you think about it, the base model is really this upper bound, right? That you should not be going over, right? That's what you do, or that's the adversarial robustness that you get if you just train a machine learning model, right? And I guess what we wanted to ensure is that jointly training both these things at the same time is not hurting our adversarial robustness in any way. And sort of we now with this orange line, that's not happening, right? We are back to where we should have been. Okay, evaluation, we plot invalidity, which is 1 minus validity. So lower invalidity is better, right? This is proximity. Again, lower proximity is better. You want to be in this part of the figure. We compare against a whole host of at that point state-of-the-art methods, and CounterNet does well in terms of both invalidity and proximity. Okay, it also runs faster. So these are your non-parametric methods, very, very slow. These are parametric methods. Again, much better, but we're doing better. We're generating better quality counterfactuals, much faster than them. And more importantly, did this joint training, because really what we are asking organizations and nonprofits to do is that don't train an off-the-shelf model and then try to explain it. Just do both things at the same time. And what we would really like to make sure is that, are we losing out in terms of predictive accuracy by optimizing all three things at the same time, as opposed to just optimizing predictive accuracy? And our results show that by optimizing all three things at the same time, our predictive accuracy does not take a hit for the most part. On some data sets, we're doing slightly better. On some data sets, we're doing slightly poorer, but we see these things as pretty much similar results, right? So CounterNet provides a way for you to leverage the knowledge of the ML model's decision boundary to achieve higher quality explanations. We do 30 to 40% better on metrics, while not coming at a cost of decreased predictive accuracy. So we don't end up sacrificing predictive accuracy as a result of that. So my sort of final take home message is that now in this pipeline, if you're trying to convince the stakeholder, if you are building an ML-based solution for them, and if it's a tabular data set, then or an image-based data set, we haven't gotten down to doing text with it. Actually, we realized that we don't need anything more than large language models to generate good quality counterfactuals for text. So text is ChatGPT takes care of generating counterfactuals for text data very nicely. So we don't need anything else. But yeah, if you're developing an ML-based solution with tabular data, maybe consider replacing your ML-based solution with something like CounterNet, because you'll be able to. Of course, there are lots of ifs, right? I mean, maybe the organization or the stakeholders don't find counterfactual explanations to be very intuitive. In that case, this wouldn't be applicable. And furthermore, if you have something that is not an ML-based solution, for example, we created POMDP-based solutions. The approach, this is just one possible approach. What we did is we use the POMDP solution to simulate training data. And then we use that training data to train CounterNet and convince the stakeholder. And we tried this in one of our papers that we wrote. Yeah, and I guess I'd like to end by saying that these prediction-aware explanations is a fertile ground. At least we're finding it to be a fertile ground for novel CS research, because you can do all sorts of things. Now we have a robust version of CounterNet, because it might be the case that somebody applies for a loan in January 2024, and they get a counterfactual explanation, and the counterfactual explanation says reduce or increase your income by 5,000 and increase your credit score by 50. That's the things that you got to do to get your loan approved. But maybe from then up until December of 2024, the bank updates their ML model, right? And now with the new ML model, maybe this explanation is no longer relevant. So even if the applicant were to make these changes, even if they were to increase their income by 5,000 and increase their credit score by 50, and they reapply, they'll still get denied. So it would be a case of the bank not honoring their commitment effectively when they gave that recourse recommendation. So that's bad. So we wanted to make CounterNet robust against these continuously shifting data distributions. We have something under prep that will go into AI stats, where we're trying to make CounterNet secure, or the explanations that are being output secure against model extraction attacks. And I'll wrap up. So I guess I'll summarize by saying that AI for social good research is very fulfilling. I've had 11 years, only 3 successes. But the sort of satisfaction that we get when we do have those 3 successes make the entire endeavor worth it. And unfortunately, the current reality is that unless you have trusted contracts in the non-profit space, it's very difficult to break into this field and do meaningful research, because convincing stakeholders is very difficult unless you have champions. Now, I'm by no means saying that if you do this, if you do explainable AI in general, then that's going to take care of everything. You still need your champions. You still need to work with tech-savvy organizations who don't need to be sold. For example, I know Faye worked with I'm assuming with food rescue organization that you worked with, they didn't need to be convinced of the merits of AI necessarily, right? Because they were already sold on the use of AI. So you still need a lot of all of the existing things that the AI for Good community is doing. But on top of that, the more you can do, because trust is a hard thing to engender in general in people, and explainable AI can go some way in helping in this regard. And I guess we sort of try to take a first step by building something which is an explainable AI method, but it is better suited for these non-profit settings where you are in the business of developing your own model, and also sort of contemplating that when we present this model to non-profits, they're going to ask us lots of questions. So we better be prepared with those answers. So as a means to apply XAI in the non-profit space. And yeah, I'll thank you so much. I should also note that we are so far this explainable AI research didn't have a domain. But now we're going to try to collaborate with the Allegheny County Department of Human Services. They have an AI model that they have deployed for the last 3 years. It's called AHA or something. And what that model does is it prioritizes homeless individuals on the basis of need, for how urgent their need is for housing. Right? So more urgent need corresponds to a higher score that the AHA model provides for homeless individuals. Less urgent need corresponds to a lower score. And a common sort of feedback that they've gotten from their homeless clients is that people want to know why is it taking 2 months for why did my friend get a house in two months, whereas I had to wait 1 year to get a house? So again, the questions that the homeless clients are posing are, why did I get the score that I got? So we're going to try to develop some explainable AI tools, and hopefully CounterNet can play a role in that. But yeah, thank you. I'd like to thank my students. These are all my students. This guy is hopefully going to be in the job market soon, and he's the one who sort of, this PhD thesis is going to be on these prediction of explanations. But yeah, thank you so much. Happy to take any questions. I know I went over time.
Thank you. Thank you, Amulya, and also thank you all for coming. Any questions? And also for people who need to go, feel free to go.
I'll push back a little bit on the point you kept making about, it's unfortunate that they rely on some champions and so on. So academia in general has a huge positive outcome bias. Right, your paper is going to get accepted only if it beats the state of the art, and so on, and that arises in like all kinds of evaluations.
Sure.
And so people either subconsciously or consciously are incentivized to, for example, train on test data or do hacking or p-hacking and so on. Like it's very, very prominent.
Absolutely.
And so now if somebody comes and tells me that, hey, on historical data my algorithm is performing very well, it doesn't mean as much as one might think. And so I don't really just trust that.
Okay.
If there is somebody who has experience in actually having deployed things and work well in practice, I might trust their word much more.
No. So I don't mean it as an unfortunate in that they shouldn't. What I meant was that it is unfortunate because this in turn ends up creating difficulties for somebody new to enter the field. Basically, that's what is unfortunate about the situation. I am not at all implying that as a field or these non-profits should not be relying on champions. You're very right. We should definitely be listening more to people who have real world experience of deploying things, etc. But it creates challenges. I think ML as a field, it's become what it has become just because TensorFlow and things like these really democratized it. It made it really easy for the high school student to sort of hack around with it and try to build something. And we don't have anything similar. Our data sets are private. We don't release them because they are protected by data sharing agreements. Nobody can sort of reproduce our results because so that's a problem, right? I mean, so that's the unfortunate part of it, basically. But yeah. Yes.
So I guess in your baselines for CounterNet, are any of those baselines more of what Cynthia Rudin would just refer to as the inherently interpretable, like just non-black box model? They say there's a lot of work on things like optimal decision trees.
Sure. No, I don't think we have that. I guess because because I think, we will not be able to get, I guess you could, but yeah, so all our baselines are effectively counterfactual explanations, other competing counterfactual explanations. We did not compare against others that were not counterfactuals. But yeah, happy to have that conversation offline in our meeting. Yes.
Can you share a little bit about your why you focus on the nonprofit segment? There's so many things to do. I think it's a very honorable thing, but it's by the definition, it's going to be a very hard, difficult shell to crack, I guess.
Well, yeah, this might, we might veer into a tangent that will take time, but I grew up my father was an army officer, and giving back to countries and giving back to society was a huge thing, right? And I ended up being a computer engineer. I ended up enrolling in a computer science degree, and I sort of said, well, how will I give back to society, right? And I just thought that, and everybody's going, my seniors are going to Googles and Amazons, and maybe the only real possibility of giving back to society is I'll earn lots of money and then I'll do some philanthropy or something, right? But this research allows me to sort of, be a computer scientist and still sort of, at least, I sleep happy at night. Whether I'm actually doing good in society or not, I don't know, right? Whether my impact is net, but I sort of can sleep happily that I try.
That's great. A follow-up. I have a personal habit to talk to the homeless people in Los Angeles, San Francisco, wherever I go. So I tend to know a bit more about their living conditions.
Sure.
And with all due respect, I just don't think scientific research is the thing that could raise up their bottom line, that could really improve their
I completely agree.
condition.
I know, I completely agree. You don't have to say with all due respect. I'm not at all implying that, science is going to get them out of, only science can, there has to be regulations, governments have to do more, right? But my stance is, if all of that additional things are happening, science can play a role in improving upon their state, upon their lives. If nothing else is happening by itself, science and scientists cannot do much. I agree, right? It's not gonna, if there's no regulation, if they still have to go sleep in the streets, right? If you don't really solve their underlying conditions, then yes, I mean these AI algorithms are not going to be able to have as much impact as they could if they were being used by supportive governments who are really taking, trying to really lift them out of their conditions, right?
Okay.
I completely concede that point. Yeah.
Thank you again. Thank you all for coming.